So about half this audience has probably seen several slides or several presentations on this, and the other half probably haven't seen anything. So I've geared it more for the half that hasn't seen anything. So apologies to those who have seen lots of the Wyoming experiment before. This is kind of a higher level introduction in terms of the experimental design, and a lot of the meat actually comes in the 3 papers after mine. So I'll defer all the good details to those guys. It's a collaboration. There's many people involved. I just want to recognize also co-authors Bruce Bowe from Weather Modification Incorporated, who is manager of the operations of this project, and Barry Lawrence, who is the overall manager of the project from the state of Wyoming. Briefly, the background, and this goes a lot toward the communications issues theme of the conference, is in terms of dealing with stakeholders and water users in the state of Wyoming. In the early 2000s, there were several inquiries from irrigation districts, conservation districts, and so forth about the state of Wyoming not having any kind of weather mod activities, partly because in the western United States, lots of the western states have weather mod programs, and so they asked about that. There was a governor's drought task force that held a special workshop on advances or the current state of the knowledge of weather mod. And in 2003, water conservation districts sent a formal application to the Wyoming Water Development Commission, the state entity, asking for a pilot project. And so the first step of that was a feasibility study, basically a desktop feasibility, meaning there wasn't any other extra data taken in it. It was performed in 2004, and out of that came the second phase of it, which essentially developed into a pilot project, which really has an applied research focus, that was funded in 2005, and it separated the tasks of the operations versus the evaluation activities. And so it's very important to have the stakeholder, be in communication, listening to the stakeholders, and also have a chance to the education aspect of interacting with them. And along that line, part of this program has been the development of a technical advisory team, which includes a lot of the agencies involved in the state of Wyoming, both in the areas that we're working, as well as generally in terms of environmental sciences. There's just a list of all the people that, or entities that are involved in that. And we meet twice a year to gather information from them, or their feedback from them, as well as provide them an update on how the project is progressing. And so the Wyoming Weather Modification Pilot Program, the evaluation side is what I'm going to concentrate on. And the primary focus, really, of the experiment is really the randomized seeding experiment, because of the need for quantitative assessment, or the desire for quantitative assessment of the weather modification or cloud seeding activities. But you don't do that it's not wise to do that as a black box type of an experiment, and so there's really the need for supporting physical studies as well, and that's particularly to examine processes that are important in the seeding concepts. The conceptual model of winter orographic cloud seeding really is fairly mature and fairly widely adopted. It's the real details of how that gets applied in specific areas that were the devil's in the details. And particularly because of the resources being concentrated more on the randomized seeding experiment, that the physical studies are more opportunistic. In other words, a lot of that is done through auxiliary studies, both using either project-related instruments or ones that become available that we can put out in the field for a couple of years, for example, that will help with either understanding the physics of the precipitation process, or validating models, for example. Numerical modeling is a large part of the evaluation, and again, it helps with the validation of the forecast model which we're using, but we can also use that in terms of plume modeling, putting into a seeding module, et cetera. You hear more about that in following talks. And collaboration, this has been a real strength of this program, is a lot of the collaborations that have taken place from other entities. Trace chemistry, taking snow samples and doing trace chemistry analysis, for example, to look at targeting. Ice nucleus concentration, or ice nucleus counter measurements that WMI has provided in one of the target areas that helps with targeting and contamination issues. Additional precipitation and weather data that's really provided by a lot of other agencies that are working in the same mountains. And airborne measurements, both early on with in situ measurements, cloud physics type stuff, but in something we'll hear about from Bart Gertz in terms of remote sensing from the University of Wyoming at looking at the physics of the clouds, as well as hydrology studies that provide some follow-on potential in terms of if there's an answer in terms of snowpack, what does that really mean for stream flow, which is really the bottom line of wanting to know what's going on. And so the Wyoming program concentrates in 3 different mountain ranges. These were chosen partly by the water users in terms of importance for different basins. It also has some background in previous studies or previous operations. The Wind River Range in west central Wyoming. It's an area with one of the highest concentrations of glaciers in North America. And it's mostly wilderness area, and so it makes it very difficult, and it's very rugged, makes it very difficult to get any ground-based observations in this area. And so I'll point out the implications of that later on. And then 2 southern mountain ranges, Sierra Madre Range and the Medicine Bow Range. The Medicine Bow Range has Elk Mountain Observatory, for example, that University of Wyoming has operated for many years, has lots of research been done there. So in the Wind River Range, because of this difficulty of making ground-based observations, the evaluation here will primarily rely on numerical modeling studies coupled with additional instrumentation or additional measurements taken in this area. But most of the resources actually are concentrated in the randomized seeding experiment, which are located in the 2 southern ranges. The randomized seeding experiment, because we're operating in these 2 ranges, the 2 ranges are close together and they are fairly well correlated. And so a crossover design, much like we heard about in the Israeli experiments, was an efficient way to attack this problem. And so the 2 ranges, they need to have similar conditions for seeding in terms of temperature, supercooled liquid, the placement of the seeding generators, for example, and then you randomly select one range or the other for seeding, and then the opposite one becomes the control. Besides the target gauge sites in each of those particular ranges, there are additional control gauge sites in each of the ranges that decrease the effects of variability in snowfall, particularly between the ranges, but also within the ranges. So there's a control area and a target area, but there's also control sites and target sites as well. Seeding period is for 4 hours. This is trying to take advantage of fairly homogeneous type of conditions as much as you can in a winter storm. Response variable is the accumulation of liquid equivalent over a 4-hour period, and then a buffer period of 4 hours in terms of trying to get the seeding material to vacate the area before the next seeding opportunity might come along. And it's fairly conservative suspension criteria in terms of this is, again, in communication with the technical advisory team and stakeholders in terms of how much snowpack is already there, how much soil moisture is there, and so forth, so you're not operating when conditions aren't so, when conditions are already has lots of water in them. Primary instrumentation, or at least resources involved in the randomized seeding experiment. These are 2 southern ranges. The red stars indicate where historical snowtail sites are. data that we used in trying to do some of the design. The green triangles are where ground-based seeding generators are located. The black squares are precipitation gauge sites that have been used in the project, and the ones that are used currently, there are 8 of them. There's 2 in each target area, for example, and then upwind and crosswind controls for both of the target areas. Other instrumentation are radiometers, one that looks at cloud conditions over the Medicine Bow out of Upper Cedar Creek, and one that looks at conditions over the Sierra Madre out of Savory. Sounding that are taken during storm events taken out of Saratoga. Example of precipitation gauge sites, there are 3 gauges, or there's 2 gauges at each site, and lots of them actually have 3 gauges, mostly in terms of data quality control for each of the gauges, because snow measurements are very difficult to make in these environments, and that's another talk later this afternoon you'll hear about. But they're in forested clearings such as this. That one's at the target area in the Sierra Madre. This is a control site, for example, down in the lower elevations in Sierra Madre. And this is in Medicine Bow Range at the forest research site there. So this is the only site that has AC power. And so we're able to run a few auxiliary instruments there as well. Radiometers is one in Upper Cedar Creek that's operated by WMI, a 2-channel radiometer that looks at the clouds over the Medicine Bows, and the one in Savory, which is a 5-channel profiler, but we actually just use it in a 2-channel mode, at least in real time, for looking at liquid water in the clouds. And then, incidentally, there is also a radiometer up in the Wind River Range that's similar to this unit in Savory. And another important aspect of determining cases, or at least in the forecasting, is the WRF RTF-DDAs run on a 3-hour cycle, 24-hour forecasts, nest down to 2 kilometers. We'll hear more about that later. So seeding criteria that needs to exist in both ranges is cold enough temperatures for silver iodide nuclei to be effective, which is, we use -8 at 700 millibars, which is roughly the altitude of the target areas. And that requires observations from radiosondes. Winds that are favorable for generators to actually affect the target areas, essentially a wind direction at 700 millibars of this, between these, from the northwest to southwest. The presence of supercooled liquid water, which come primarily from microwave radiometer, and or indications from the model, as well as observations, cloud observations visually or satellite derived. And of course, no suspension criteria in effect in order to have a call case, essentially. So then once those kind of conditions exist, the operators go on to a web-based case management tool that provides them with the randomized selection of which range to seed, and it also allows them to log in which generators were turned on or which ones might have had a problem or so forth. So the overview of the design is it's a randomized experiment in the 2 southern ranges. You need to have a similarity of storm conditions for a crossover design, and the ability to have a crossover design results in a very statistically efficient way to conduct and evaluate the seeding experiment. In practice, however, there are some issues in terms of consistent selection of cases, and that's something that we continue to evaluate, that we think we're doing a pretty good job on that. Measurement of precipitation, which has some challenges I've talked about. The usual kind of things, which are really important. Seeding plumes affecting the target area, and potential contamination between the ranges, for example, are issues that need to be addressed kind of in these physical studies. For example, as I pointed out before, ice nucleus plume detection on the ground are being made or have been made, and snow sampling for trace chemistry analysis to look at if the snowpack actually has elevated levels of silver during seeded conditions. The statistical design relies on the ratio test, actually the root regression ratio, which means that it has some control, has the ability to put control gauges in there. The null hypothesis, of course, is that it's 1. In other words, you're looking for conditions where the ratio is significantly different than 1. And the good thing about this, and we've seen this in the Israeli project as well, is that it provides direct information about the proportion of increase, 10%, 12%, whatever it is. I won't go too much into the sampling size factors, but you need to know how many samples is reasonable for a given set of parameters. And for example, in this experiment with reasonable correlations and variance that we had determined beforehand, we came up with a value, at least if the difference were 15%, you'd need 166 cases. But you can see that it varies quite strongly, non-linearly, as correlations change, for example. The number of cases that we actually get, there are a host of ways to try to figure that out ahead of time, although we didn't have the kind of data that we would have been great for. But essentially, we're getting on the order of 30 to 40 cases per year. I think I can skip through this one to go to this. So the pilot program developed on request of stakeholders, and that really points out the importance of fostering continued communications and education. The project is in 3 target ranges. The experimental design is in 2 southern ranges. There are resources available for the generators, for seeding, which is the generators for the decision-making process, and for the evaluation. And numerical model advances are really important for the evaluation. We'll hear about that a little bit. And it also provides a great opportunity for ongoing collaborations and physical studies, which we'll hear a little bit more about that as well. Thank you.
Time for one really quick question. Don?
Have you published your design in some formal paper of some kind? Because that always seems to be a question when you get to these sort of things. What did you say in your design?
Right. The experimental design, yes, we have our experimental design published, and it's not published in a it's being written for a peer review right now. It actually has been peer reviewed in terms of setting up the design, but it will be published in perhaps in BAMS, that's what we're looking for, or maybe in the Journal of Weather Modification. The design already has been set in stone, basically, on a report to the Wyoming Water Development Commission, but that needs to be formalized and shrunk down quite a bit to put into publication.